You awake? Lesson 5 says, many body problems. What we're going to ask ourselves today is, what if you got more than one mass? But first, it says video Big Bang Theory. We just watched that. I want to do a little demonstration. Pause the video. So the question we're asking is it possible to hold something against a wall without pushing up on it? If I represent the mass with a dot, we would get something like this. What are the forces acting on that book? Get the obvious one. Okay. Was the book accelerating downwards? No. Was the book accelerating upwards? No. So what does that mean? It means in the vertical direction, forces must be, looking for a word that begins with letter B. So there must be an arrow pointing up the same length as mg. I'm not quite sure what that upward force is yet. I'll come back to that. I have a suspicion, but what else? Well, I was pushing against the wall, and let's pretend I was pushing to the right. We'll call that the applied force, and this was me. Okay, if I push against the wall, what does the wall do? Pushes back, same size. This is a Newton's third law. Forces come in pairs, except we've given the force that a surface pushes back at you with a special name. What force have we called the force that a surface pushes back with? It's a normal force. Usually we've had our normal forces pointing straight up, but Linnea, that's because our ground has been flat. Now I've made the ground vertical, so the normal force has become horizontal. Does that give you any suggestions for what that upwards Friction. So my apologies to those of you on YouTube. I'm going to be walking away from my recorder for a little bit. The harder I push, the more friction there is. And in fact, as I ease up, if I don't push as hard, what happens to the normal force? Gets bigger or gets smaller? Smaller. And since friction is mu times the normal force, can you see it just right now friction is becoming less than gravity? You do this all the time without realizing it. Whenever you carry something like this, when I carry something like this, think about it. Which way am I squeezing? Inwards. But what force am I resisting? Vertical. How? The harder I squeeze, the bigger the normal force out, the bigger friction, and I'm safe. But if I relax my fingers, I can just feel it right now. It's at the equilibrium point, and there it was. Now, you've all figured out how to carry something since you were like 3 years old. But there's the physics of it. You can, it turns out, resist a vertical force without pushing up. By pushing inwards, as long as you got friction. It's also why ice cubes are so tough to carry. Not much friction. So you'd have to squeeze. Actually, professional people who are moving ice blocks, they have these really sharp calipers that they use, these tongs. That's how they carry them, because to try and use straight friction would be tricky. Is that okay? Just a little thought experiment. Also kind of a cool free body diagram. All right, now on to the actual lesson. Many body problems. In these problems, we have more than one mass connected together by strings. There's various ways to do this. I've seen some people teach this where you always end up using a system of equations and you substitute one equation into another equation. I would prefer to just expand our winner minus loser approach, and we're going to do that. I wrote here, the easy approach is to realize we can treat this whole system as a single object, because if they're attached by a string, they must be accelerating at the same rate. Here's what I mean. Look up. Here are two objects attached by a string. If the object in my right hand on your left is accelerating at 2 meters per second squared, you know what this object is also accelerating at? 2 meters per second squared. We're not, Reese, we're not going to let you do this. No jerks in my classroom. That turns out, by the way, that right there is really tough to analyze. You need calculus. You need some fairly heavy-duty calculus. If you yank on something, we give it a name. The proper name in physics is called a jerk. And if you do that, it's really tough. So as long as we're pulling smoothly or accelerating smoothly, I'm going to argue there's no way for one mass to accelerate different from another mass if they're attached by a string. You okay with that, Sydney? They're strings. That's how they work. So, the easiest is just to jump into a question. Example 1, I like example 1, I like example 1, I like example 1. Example 1 is a nice question. Ange, what does example 1 want me to find? Nice and loud. And? Okay. And you're probably going to do it in that order. In fact, our strategy for most of these many-body problems is we're going to zoom out, we're going to find the overall acceleration, and then if you want specific forces like tension or friction or whatever, we'll zoom into one mass and we'll write an equation for one mass. Okay? Is there friction in this question? What's mu? I don't know. What's mu with you? I said, to start, let's put it on ice. We could add friction later. In fact, in Physics 12, we'll always add friction, just adds an extra force. It doesn't make it any tougher, Christine, it just makes the question a little longer. So what's the solution? We're going to treat this system as a single object, and we're going to write force equations. Say, what? Show you what I mean. Up on this first diagram, Christina, we're going to do a free body diagram, and let's start on the very left and work our way across the page. So let's start with the 3. What are the forces acting on it? Get the obvious one. What do we usually label that as? Is there more than one mass in this question? Say yes. So you know what? I'm going to go M1G. You know what I'm going to call the second mass? M2. And I typically label them from left to right so that, Natasha, all of our work looks the same. There's no rule for that. It's just, I'll call the first one starting from the left M1, M2, M3, M4 as I go across the page. You don't have to. It's not a rule. I won't mark you wrong if you label them a different order. Just be consistent in your work. Is mass 1 sinking to the ground like quicksand? Is it flying at you like Superman? So what do we call this vertical force right here, Christina? Is there more than one mass? I'm going to call it normal force number 1 to go with mass number 1. I think that's being organized and writing as little as possible. What else? Well, this thing is accelerating to the right, I think, because it's on ice. What's pulling it to the right? Not the 20. That 20 way over there isn't even touching it. You know what's pulling it to the right? The piece of string. What have we called the force that a piece of string exerts? Tension. Like you're feeling right now. Okay, sorry. So I'm going to just put an arrow on the string and label that with a little t. Those are the 3 forces that are acting on mass 1. Sydney, let's you and I do mass 2 together. See it, see it, see it? Mass 2 is going to be a tiny bit trickier, but not much. What are the forces acting on mass 2? Get the obvious one. I'll call that M2G. Is it sinking in the ground like quicksand? Is it flying in like Superman? No, no. So I think there's going to be a normal force number 2. You agree with me there? Okay. This 20 newtons to the right, this is something off the page pulling. Who remembers what our generic term for something off the page pulling, applying a force was? Yeah, if applied, I even used the word. Okay, so here I'll call this if applied. There's one more force, Sydney. Is there a string attached on the left-hand side of this mass? Well, believe it or not, tension is pulling that way. That right there in the middle is actually a forces come in pairs little situation, but both of them are feeling tension. The 3 kilogram is being pulled forward by tension. The 2 kilogram is being slowed down by tension. And now we're going to put it all together. I said the solution is we treat this system as a single object and we write a single force equation. Daniela, here's what I mean. Which way is this whole thing accelerating if it's on ice? I think you agree with me? Okay. Who's winning then? Anything that points to the right. Who's losing? Anything that points to the... Let's start on the very, very right and we're going to write an equation. Who's winning? And now what we're going to do is we're going to walk along the rope, the string. So as I walk along the string, I hit a T, tension. Winner or loser, which way is it pointing? loser minus tension. Da-na-na-na-na-na-na-na-na-na. Winner, huh? Winner plus? Any other forces along the string? I don't care about the mg's. They're not in the direction that I'm writing my equation. Equals, and here is going to be the difference. It's almost ma. Have we just taken forces from more than one mass on the left-hand side? Yeah, these are from mass 2. This is from mass 1. Have I got more than one mass included on the left-hand side? Well, then I better have more than one mass included on the right. That's the tweak. And that's what I meant, Natasha, when I said, oh, you treat it like one big ubermass. 5 is what's going to go there eventually. 3 kilograms plus 2 kilograms. Hey, Daniela, what's minus t plus t? I love these questions. And do you know why I love these questions? Because every time I do these questions, I find them relaxing. Do you know why I find them relaxing? Because I lose tension. No? Really? Too soon? So, you can do that. Ange, I'm coming back to you. What did this question want me to find first? Oh, how would I get the A by itself? What's that bracket doing to the A? Timesing. So how will I move that whole bracket over? Divide. And my formula manipulation skills give me a little nerdy smile, and I say that could have been really ugly, but it turns out it's kind of clean. The acceleration is going to be the applied force divided by both masses. And I bet you can even do this in your head. How big is the applied force as a number from the diagram? 20 divided by, how big is mass 1 from the diagram? Plus, how big is mass 2? Having a tough time writing right there. Let's try that again. There we go. In your head, what's 20 divided by 5? Look at that. I'll go 4.0 because I think everything went to 2 sig figs. And it's an acceleration, units. Folks, that's really the whole lesson, almost. Oh, wait a minute, no. You said there was something else it wanted me to find. Acceleration and? Pat, specific forces, tension, we're going to look at one mass. Do you want to use mass 1? Let's use mass 1, okay? Doesn't matter, but I notice mass 1 has less arrows on it, which might mean it's simpler. You'll get the same answer for mass 2, and I'll prove it in a second. So look at mass 1. Which way is mass 1 accelerating? I've scrolled, you know what, let's rewrite the free body diagram. We had M1G, normal force 1, tension. Is that okay? Yeah. Okay. Which way is this accelerating? To the? Who's winning? Tension. Who's losing? No one. Now, can you see if I added friction to this equation, I would just have one more force pointing that way. It would be mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force, M1G. In other words, Haley, adding friction is kind of a meh. It's more work, more typing, but not really a huge level of difficulty. What does winner minus loser always equal? Do we have forces from more than one mass this time, or just from one mass? Which one? So M1A. Pat, how big was M1? And what was A? In your head, without a calculator and a nerdy smile on your face, how many newtons must tension be? Yep. Mr. Duick, what if I used M2? That's a great question. Now, M2's got more forces on it, but I could have used M2. Thomas, let's do M2 for consistency. Let's quickly on the next page redo the free body. It was M2G, yes? And normal force 2, and we had applied and tension was that way. I think? Yeah, okay. Which way is mass 2 accelerating? To the right. So who's winning? To the right. So I guess applied. Any loser? Minus the tension. What does winner minus loser always equal? MA. Did we have the forces from more than one mass this time? No. Which mass are we writing forces for? Mass number 2. So it's going to be M2A. We're trying to find tension. What's right in front of the letter T that I don't like? Plus that to that side. We've done this little dance before where we swap 2 around, right? And I get F applied minus M2A equals tension. Let's plug in numbers. How big was F applied, Thomas, my friend? 20. Minus M2 was 2. How big was the acceleration? Oh, in your head, Thomas, 20 minus 2 times 4. Is that the same answer that we got earlier for mass 1? So the tension is the same, and we've just proved it. So from now on, Lyndon, pick whichever mass is easier to find the individual force. I'll give you full marks for whichever one you use, but be lazy. Give me 1 second here. You good, Jenna? This is our strategy. You have more than one mass? No, you don't. Pretend it's just one big uber mass. Write an equation for everything, and the equation is going to be, Connor, along the string. We can even have a hanging mass, like this. If we do this, we need to understand what's causing this to accelerate, I think, is gravity, weight. Can I use the word weight? The weight of this is pulling everything down. There's no way this is moving to the left on its own. There's no motor or anything like that. It's going to all slide to the right and down. This is why, by the way, at the beginning of this unit, I told you we're not always going to have right be positive and down be negative, because here we have to the right and down in the same question. It would be, which way do you want to be positive? Whichever way, Daniela, is more convenient. That's what we'll let be positive. You ready? Here we go. It says find the acceleration and the chord tension. Okay. What's our strategy going to be? We're going to find the acceleration first by Taylor writing a big equation for everything. And then we'll go look at individual masses to find individual forces like tension. Okay? Good yawn? Here we go. Natasha, this first mass here, let's do the free body diagram. What are the forces acting on it? Get the obvious one. Hang on 1 second. Pause the video. Keep going. Natasha, what are the forces acting on it? Get the obvious one. Okay? Is there gravity if it's sitting on tires? Yeah, still, I think the tires are meant to say no friction. It's going to roll. Because I didn't put a mu equals 0, but I think it's reasonable to assume this is a perfect little car. Is there more than one mass in this question? I'll call this one M1G. Is it sinking to the ground like quicksand? Is it flying here like Superman? So? And I'll call it normal force number 1 to go with mass number 1. What else? Is there friction? Say no. Is there a rope? What's the special name that we give to a force from a rope? Like you're feeling right now for being late. No? Okay. Now, the cool thing about a pulley like this is it can change the direction of a force. So we're going to follow along the string in just a second, but let's keep going, Natasha. Let's do a free body diagram for the second mass. What are the forces acting on it? Get the obvious one. Start to see why I go so systematically? I think it helps. Is there more than one mass? So what will I call this one? M2G. The mass is changing, not G, right? Is there a rope? Which way is tension pointing? Upwards? Is there a normal force? Is this sitting on a surface? So no normal force. Kids kind of get normal force loopy. No. Okay, there's our diagram. Now let's get our equation. Who's winning? I think the only possible situation here, Natasha, is this whole thing is going like that. So what's causing this in the first place? I think that. So here's what I'm going to say. Michael, I'm going to follow, Mike, every single force along the string, and anything that ends up pointing downwards when it gets to the bottom is going to be a winner plus. Anything that ends up pointing upwards when it gets to the bottom is going to be a loser minus. Boy, that was really aggressive. So, ready, Natasha? Let's keep going. Who's winning? More specific. Which force in my free body diagram is winning? Thank you, because I have nothing on my free body diagram that says the second that. Okay, good. M2G, and you've just committed to what's positive, what's winning. Now let's walk along the rope. Oh, this tension here, winner or loser? Minus. Now this tension here, you might think, well, follow it. When it gets to this side and down here, which way would it end up pointing? Down, which you have decided is a, yep. Are there any other forces along the string? Now kids want to put some of these gravities, no, those are in different directions. They're not along the rope. Okay. Are there any other forces along the rope? Say no. Good. So what does winner minus loser always equal? Well, normally it always equals MA, but we pause. Do I have forces on the left-hand side from more than one mass? Then I better have more than one mass. It's going to be Natasha, you starting to relax? I'm starting to relax. Do you know why I'm feeling relaxed? Why am I feeling relaxed, folks? Oh, I'm losing tension, baby. Ooh, I like that. What was the first thing this wanted me to find, Natasha? Find the? What was the first thing it wanted me to find? Find the? Oh. How would I get the A by itself? What's that bracket doing to the A? What's that bracket doing to the A, folks? Multiplying. So how will I move that whole bracket over? Divide! Really? Okay. So if I hear you, you're telling me that the M2G would just drop down like a domino. I would divide the M2G by the bracket, M1 plus M2. Natasha, that's actually equals A, but do you mind? I'm going to put A equals because that's where we're used to seeing the A by itself. Hey, let's finish it off, you and I. What's M2? Now it's plug and chug. How big is M2? Yep. How big is G? You know this. It's not on your you know this one. 9.8. Good. Divided by, how big is M1? 6 plus 2.5. Natasha, is this a fraction? Say yes. Is there more than one thing on the top? I might need to put the top in brackets. I definitely need to put the bottom in brackets because they're separated by a plus sign. Get your calculators out. Practice typing this in, please. Oh, pause. Built-in error check. Look up. Suppose the rope was cut. What's the maximum acceleration this thing could possibly have if it was in free fall? 9.8. Is it in free fall or is there a rope attached to it? If you get an answer bigger than 9.8, you've screwed up. There's a bit of a built-in error check. I know the answer's got to be less than 9.8. Has to be. Okay. Do this one in your head, Mr. Dewick. I don't know if I can this one. 2.5 times 9.8 divided by bracket 6 plus 2.5. What'd you get? I'm asking someone who I don't think has a calculator here. What'd you get? I'm asking someone who I don't think has a calculator here. What'd you get? I'm asking someone who I don't think has a calculator here. Folks, you got to bring your calculators. We're going to reach the point now where trying to do this in your head is unlikely. I got 2.8823. You know what? 2.88, 2.9. Yes? Units, it's an acceleration. Don't turn the page yet. We're not done. Units, it's an acceleration. Meters per second squared. Gurjot, please read the original question. It said, find the acceleration and what? Gurjot, let's find the chord tension, you and I together. It doesn't matter which mass you want to use. Do you want to use mass 1 or mass 2? I don't care. Pick. Mass 1, you say? Okay. So let's do an equation for mass 1. Which way is mass 1 accelerating? I think to the right. So who's winning? Let's call this part A for acceleration, B, tension. Sorry, who's winning? What did you just say? Who's losing? It's a trick question. No one. What does winner minus loser always equal? Oh, and it's going to be M1A. Good. See, this is, now we got to be careful with our masses. Yes? M1A. Do I know mass 1? 6. Do I know A? I just calculated it. Of course, you know I'm going to use my answer button because it's more accurate because this is a rounded off value. So you're saying I can go 6 times that? And I get 17.3. 17.3 what, Gurjot? It's a force, newtons. Have we answered the question now? Well, now we can turn the page. We can even handle questions with friction. Really? Yeah. Darcy, how do you know there's friction in example 4? Yeah, I stuck a little mu on there. That's my high-tech system. Or, if it's a word problem, I might say, is sitting on a rough surface. That's my code. Okay. This is the same question we just did, except no wheels. All right. Let's do a free body diagram. Oh, Gurjot, what does it want me to find? And? So let's make sure I find both. On a test, by the way, I would make sure I put a part A and a part B to get your attention. But here, I can improve your reading skills, right? Hey, Darce, what are the forces acting on this first mass? Get the obvious one. I totally agree. Is there more than one mass? I'll call this M1G. Is it sinking into the ground like quicksand? Is it flying into you like Superman? So I think there's a normal force pointing up the same size as M1G. I'll call it normal force number 1. What else? I agree. Which way? And I typically just label it right on the string rather than drawing a completely separate arrow. I don't know why. You could draw a completely separate arrow, Tristan. I'd give you full marks, but the string is there. It's handy. What else? Which way? Yep. I think that's all of them on that mass. Tristan, let's look at the 2.8. What are the forces acting on it? Get the obvious one. Which way? Is there more than one mass? So what will I call this? Not just MG, but? Yep. That little bit of organization, by the way, folks, is so minimal, but it's so worth it. It's so worth it. What else? Which way? Yep. Is there a normal force on this guy? Is it sitting on a surface?
No.
Oh, okay. Cool. Who's winning? Is there any way that magically this could on its own start crawling on its own to the left? So either we're sliding down, or it is possible that this could be so heavy that this is just dangling and nothing's accelerating. And we'll do one like that, and I'll show you how you can recognize that that's happening. But for now, let's assume that that is our winner. So Reese, who's winning? I didn't hear you. I'm sorry? Just read me that. That's not, I don't care about numbers. We're going just abstract, generic right now. So, Reese, let's get the equation. You said M2G is winning, and now let's walk around the rope. This tension, winner or loser? You decided that this was a winner, so pointing down is a winner. This tension is pointing up, so it's a minus. Keep walking around the rope. This tension here, if it came around, it would end up pointing down. So this tension is a winner plus. Good. Friction. Follow it, follow it, follow it. I think if friction ended up here, it would end up pointing up. Yes? Got to use your imagination. But yeah? So it's a loser? Oh, you know what? Look up. Let's call this friction force 1 to go with mass number 1. If I mass number 2 with friction, I'll call it friction force number 2, just so that we can really be organized. So I'm going to go minus friction force from mass number 1. Reese, are there any other forces along the rope, along the string? Nope. There's other stuff, but don't care about that. Equals what? Equals what? Winner minus loser in this equation equals what? Why? Because we do have forces from more than one mass on the left. We better have more than one mass on the right, which I think kind of makes some consistent sense. Yes? Reese, raise your left hand nice and high in the air. Seriously. Raise your right hand nice and high in the air. Seriously. Stretch. Relax. Oh, why can we stretch and relax, folks? Oh, I love these questions. I'm just, this is like a little mini spa. I can just feel the tension ebbing away. By the way, what that also means is you can't find tension by looking at both masses, because tension will cancel every time. Reese, what's the first thing this question wanted me to find? Find the... Oh, how would I get the A by itself? How would I move that bracket over? What's the bracket doing to the A? Adding, subtracting, multiplying, or dividing? So I'll move the bracket over by dividing. Okay. So I think the M2G is going to drop down like a domino. The minus friction force number 1 is going to drop down like a domino. It's going to be divided by M1 plus M2. And that equals A. Let's keep going. I don't think we can quite plug and chug here yet, because it's going to look like this. M2G minus friction is what times what? So it's going to be mu times normal force number 1, because it's friction force number 1. I don't know normal force number 1. Oh, but look. I know another force the same size as normal force number 1 from my free body diagram. What force must be the same size? M1G. You got to be careful now, right? Okay, so I'm going to get this. M2G minus mu M1G all over M1 plus M2. And this, Christine, is why I said to you earlier, I don't know if friction makes it as much all that tougher as, more typing and a bit longer. Is there a fraction here? Yeah. Is there more than one thing on the top? Yeah. Brackets. Is there one thing on the bottom? Yeah. This is tough enough, though. Let's carefully plug in numbers. The acceleration is going to be, I've scrolled down. What was M2? I don't have these memorized. What was M2? 2.8? Natasha, what's G? Okay, you're back. Good. I figured you had that. Minus, what's mu? I don't know. What's mu with you? What was mu? 0.12. Mass 1? 3.2. G, 9.8. 3.2 plus 2.8. You know what? I'm going to want this on my calculator too, so let's type it in a hurry here, Mr. Dewick. Bracket 2.8 times 9.8. I don't use brackets to show multiplying on my calculator. Minus 0.12 times 3.2 times 9.8, close bracket, divided by 3.2 plus 2.8. Some of you have the nice calculators that let you do a top level and a bottom level in your fractions, which means you won't need the brackets the way I do. Do you get 3.9461333 repeating? Yeah? So I'm going to write 3.95, but I'm going to store this on my calculator. 3.95, Reese, final bit, acceleration, units. I agree with you totally. Gurjot, are we done? Oh, what else do they want me to find? Okay. Luke, which mass has less forces and junk on it? I think I would find tension using mass 2. I think it'll be cleaner. Okay? So look at mass 2, Luke. I got to scroll down. You have it in front of you. Who's winning? Who's losing? What does that always equal? Well, it equals some variation of MA, but this time it's going to be, yeah. What's right in front of the T that I don't like? You know what? We've done this little dance before. So I think we're going to get this. M2G minus M2A. That equals tension. M2 was 2.8 times G minus 2.8 times, answer button. And I get a tension of 16.4 newtons. Wow, I am going to finish this lesson. I didn't think I would. Okay. Hey, we can even handle more than 2 masses. We can. Kieran, you ready? Here we go. Let's start on the very, very left. What are the forces acting on the 1 kilogram mass? Get the obvious one. I totally agree. Oh, yeah, let's call it M1. Sure. What else? Pause. Look at this diagram. Is there more than one rope in this diagram? I think there is. One rope on the left-hand side and one rope on the right-hand side. So let me ask again. Is there more than one rope in this question? Is there going to be more than one tension in this question? Tension 1. I'll call the other one tension 2. Yeah, okay, here we go. Let's keep going. I think that's it there. This big mass in the middle, what are the forces acting on it? Get the obvious one. I'll call that M2G. What else? Which tension, where, direction, which way? First of all, let's go in order. Is it sinking into the ground like quick? Is it flying in like? So there's going to be a normal force, and I'm going to call that normal force number 2 to go with mass number 2. I guess there's a tension pulling it to the right, and that's tension 2. I guess there's a tension pulling it to the left, and that's tension 1. On the other mass. I think you stuck yours on there already. You were all eager. Now, Kieran, how big is this mass? How big is this mass? Which way is this likely to be accelerating? I think the bigger mass is going to be pulling everything down. So I think it's going to be sliding to the right. And I had to ask myself that because if it's sliding to the right, which way is friction pointing? To the left. If this was the bigger mass, I would have it sliding to the left, and I would have friction pointing to the right. But here, I'm pretty sure there's also going to be, and I'll call it friction force number, not number 1, number 2, to go with mass number 2. Have I missed anything on that big mass in the middle? I got both strings. I got gravity. I got normal force. I got friction. I think that's it. Right-hand mass, Kieran. What are the forces acting on the 8? Get the obvious one. I think that's what you said.
Which one? Same rope. Both tension 2s. Who's winning? I think M3G. Anything, if I follow it all the way through this diagram, that ends up pointing down on the left-hand side will be winner plus. Anything that ends up pointing up on the left-hand side will be loser minus. Okay, so here's our big Uber equation. It's going to be M3G, and now we walk along the ropes, plural. Tension 2 here, winner or loser? Loser. You say that so casually, it just slips off your tongue. Loser. Okay. What about this tension 2? Follow it, follow it, follow it, follow it. It ends up pointing down, which makes it winner plus. Then I run into tension 1. This one here, I think if I follow it all the way over to here, it would end up pointing up still. Yes? So it's going to be a loser minus. What about friction force? Winner or loser? Loser. Friction force number 2. Then I have this, got those? This tension 1. Now again, it looks like it's pointing in the same direction as this tension 2. You might be tempted to make it a loser, but if you follow it, I think when it went around this corner, it would end up pointing down, would it not? So it's going to be a winner plus. And M1G, again, you might be tempted to say, well, it's pointing down like M3G, so it's a winner. But I think if you follow it, when it turns the corner, and when it turns the corner, when that arrow gets over here, it ends up pointing upwards. It's a loser minus. Do I have forces from more than one mass on the left? So on the right, what would it be? You know what? I'm lazy. M all times A. And if you want to, you can use that as your generic shortcut, because that also works for M1 plus M2. In fact, it works for all. Kieran, we got our big equation. Do you feel relaxed? I do. Do you know why I'm feeling so relaxed? Oh, I'm losing tension. I'm losing more tension. Oh, I can just feel the tension leaving my body. I like that. How would I get the A by itself? So the M2G drops down, the minus friction force 2 drops down, the minus M1G drops down, M3G, I can't read my own writing, that's a problem. Be organized and make sure you can read your own writing. Divide by M all, and that equals A. That's going to be M3G minus friction force 2. Well, don't write this down, just look up. In my head, Kieran, I would say, well, that's going to be mu times normal force number 2, but I don't know the normal force. Oh, but look at my free body diagram. I know another force that has to be the same size as normal force number 2. Which one? So I can, as a shortcut here, because this isn't too hideously complicated, just go straight to M2G and then minus M1G all over M all. We'll pick up with this Thursday. I'll spend a few minutes finishing this off Thursday, because I did promise you I would give you some time to work on lesson 4. Also Thursday, you're going to get a take-home quiz. The take-home quiz is going to have everything up to and including lesson 4 friction, so it won't have anything with more than one mass. But everything else is fair game. The take-home quiz is going to have some nasties to you, but you're going to find that when we go over them, oh, really, Mr. Dewick? We can handle that? That's it? And someone, I can't remember who was talking to me this morning, that's where we're at the stage where everything right now seems really tough, but if we work our brain through it, hopefully it'll all fall apart. Okay?